Hello. Hey, good evening, everyone. Welcome to my talk. There's a lot of resources already available about how to write awesome code, like clean code and like code smells, things you shouldn't do, how you can really optimize your code. But the same doesn't quite exist for unit tests, right? So that's what I would like to cover in this talk. We'll have a look at like why do we write unit tests, but also how can we make them truly awesome. So before we get started, a small little word about myself. So I'm Jeroen, I'm Belgium. I'm currently the lead Android developer for Philips Hue, the biggest and coolest IoT system in the world. And I'm also quite active on Twitter at @molsjeroen, so feel free to follow me there. So what we're going to cover today is basically the following. So I'm going to talk to you a bit about the core principles, why we actually write tests, what the ground rules for making truly amazing tests are, and then we're actually going to look at concepts like code coverage or test-driven development, debunk some testing myths, compare test code with production code. So we're going to really take tests and see how we can improve them, and then we're going to wrap it all up with some tips. All right, so the core principles. So let's start simple. Why do we actually write tests? So first and foremost, you write tests to be able to prove that your code is doing what it's supposed to do, right? But also, your code should keep on doing what it's supposed to do over time. So the test can actually make sure that your app keeps on working. Furthermore, but this is a bit tricky, but if you do it right, tests can actually serve as documentation. It will enable you to refactor later on. It will enable you to release faster. And unit testing is also simply the easiest form of testing. But if you really put it all together, the main reason why you write tests is to run them. Because the more you're going to run your tests, the more value you're actually going to get out of them. So this is the first core principle. Secondly, testing is a long-term commitment. Because if a test fails, you're going to have to go and fix it. If you change, if you're going to refactor your code, you're also going to have to refactor your tests. If you're going to remove some code, you need to remove obsolete tests. If your testing framework gets a new update, you'll have to go and update that. So there's plenty of stuff you need to do in order to keep your tests alive. So test code is exactly the same as any other line of production code that you have. And then finally, if you want to be serious about testing, you're also going to need to be serious about tooling. Tests require infrastructure to run. For instance, if you want to run all of your tests on pull requests, you need to have a CI server that automatically does that. If you're going to run your tests often, they need to run super fast, or you're going to need to do some Gradle optimizations to make them work properly. Maybe you want to investigate how your code coverage is evolving over time, so you need a tool to analyze code coverage, and so on and so on. So what all of these tools actually will do is they're going to help you optimize your tests for failure. Because if you run your tests, you'll get value out of them because you know everything is still working. But when they fail, that's when you really get more value out of them because then you really know like, oh, something stopped working and you can take action on that. And in order to take quick action, you need to optimize them for failure. So what are the 3 basic rules that make tests truly awesome? So first and foremost, your tests need to be fast. Not just a little bit fast, but really ludicrously fast. You need to be able to run all of your tests, like thousands of tests, you need to be able to run them in under 1 second. Because the faster tests are, the more often you're going to run them, because it's not really a burden to run them anyway, right? And the more you run them, the quicker you're going to actually find bugs, and the quicker you find a bug, the easier it will be to fix it. So tests really need to run super, super fast, so you're going to run them on every single line of code changed. That means that we don't want to have stuff like sleeps or waits in our tests. We also don't want to test file or database operations. We don't want to test actual network requests, because all of that is simply too slow. And finally, you don't want your unit tests to run on an Android emulator or Android device, because even those tests, they're way slower than plain JVM tests. Secondly, your tests need to be small and focused. By small, I mean physically small. That means only a few lines of code. So that if you go to the test, that you just like in one look of the eye can see what's actually going on. That's what I mean with small. But they should also be focused. So every single test should only test one specific part of your code base. Or flip it around. If there is a bug in your code, then only exactly one test should fail. So for instance, this would be a good test. Login should fail with wrong password. This is pretty straightforward, right? It tests one niche use case of your app. Lastly, tests should be 100% reliable. Imagine this. So you're running your tests on your CI, and your CI fails. So then the single most important thing you have to do is you need to drop everything, go and look at the CI and fix the failure, right? But what if you then start investigating the failure? You see it's like, yeah, this test case has failed, okay, fine. You start looking into it and start seeing what's going on, and yeah, you spend a few hours and you really can't find the problem. So then you're desperate, and what you do is you just, let's rerun the tests again, and then suddenly they pass. That drives you mad, right? These random failures will make you lose trust in your safety net. Because if this happens once, then you're going to be like, okay, if it happens twice or a third time, then you're going to start assuming like, oh, it's going to be the failing test again. So yeah, I'm going to look in it later. So you're actually going to start losing trust in your safety net. And if you don't trust your safety net, you're not going to take any risks anymore, right? If you don't trust your safety net, you're not going to refactor things anymore. You're not going to aggressively drive things forward anymore. And this is one of the key advantages of unit tests. So let's, for instance, look at this test. What we do here is we have a time formatter, and we're actually testing that it properly formats the current time. Now, this actually, it's not a great test. Because if you look at this, what we first do is we calculate the expected time. So we use a date object to calculate the expected time. Then we call our time format and have it calculate like the format for the current time. And then we compare if both of them are equal. But both of these statements actually internally use a different date object. So they refer to a slightly different timestamp on your device. So that means if you run this test, it's probably going to pass. If you run it 100 times, it's probably going to pass 99 times and fail once. So this is like a very subtle timing issue baked into your test, actually. So we can actually make this test stable by simply injecting the date into the time formatter. So if the date is injected, they both use the same object, and then fine. Now the test is predictable. And thanks to Kotlin, you can very easily make the date object a default parameter, and then you don't even see it in your production code. So that was it about like the 3 ground rules. So tests should be super fast, they should be small and focused, and 100% reliable. Now, let's have a look at code coverage. Question to you. So if your app has 100% code coverage, I'm talking about unit tests, can your app still have any bugs? Who thinks that your app can still have any bugs if you have 100% code coverage? Good. So the majority thinks that. And that's true, because if you have 100% code coverage, plenty of things can still go wrong, right? If all of your classes have 100% coverage, yeah, they can still, in the way they work together, there could still be issues, right? So at least you need an integration test. Or if you have the UI, the background color could be wrong, you could be using the wrong font, like the paddings margins could be wrong, so also there stuff could go wrong. And if you're talking to some external service, like most apps do, well, your REST endpoint could actually return you something unexpected. So also there, it could fail. But let's make this problem slightly smaller. Because if we just zoom in on one specific class, if that class has 100% code coverage, it can't have any bugs, right? Who thinks that a class can still have any bugs if it has 100% code coverage? Ooh, really good. Maybe slightly less people, but still quite a lot. Let's look at an example to basically analyze this. So we have this very complex class, a calculator, and we write a test for it, which is amazing because this single test basically causes the entire code coverage to be 100%. We touch the class, we touch the method, and we touch the line, so it's just 100% code coverage across the board. But what happens if I remove the assert from the test? Then my code coverage is still 100%. Because the code coverage tool, all it does is, it just looks if your tests are actually calling certain lines of code. It can't check whether your asserts are meaningful. Even more, if we change the implementation of the calculator and we just put 4 there, then this test still passes. We still have 100% coverage, but you could argue that this isn't really a useful calculator, right? So 100% code coverage is meaningless. It doesn't tell you anything about the quality of your tests. It's completely unaware of the functional coverage, and it doesn't even check whether you're doing meaningful asserts or not. But it's even worse than that, because if code coverage would be meaningful, then it still wouldn't be a good idea to try and get 100% code coverage. Because while you can test almost anything, and I mean that, you can really test almost anything, at some point, just the effort required to make something testable is so big that it's just, there's hardly any return on investment. Like, for instance, what I did a while back is, we had this use case where actually, if our app goes to the background and to the foreground back within like 3 seconds, then we didn't want to stop all of like our ongoing operations in the background. So I made this nice little threading clause that like, yeah, if the on resume on pause would happen in like within 3 seconds, then it wouldn't stop everything. And I completely wrote tests for that. But it's so complex and it took me so much time to write it. I then had to build in like a lot of sleeps and waits, and I had to modify timings just to make it testable, but it's, the benefits you would get from that are really, really small. So even if code coverage would be meaningful, still 100% isn't, yeah, it's just not practical to try and get. So what is code coverage useful for then? Well, it's definitely not useful for your manager, right? If your manager asks you, hey, you need 100% code coverage, then just download some tool that generates tests on the fly, install that, show them the numbers, and then you're good to go, claim your bonus, and then you can go back to doing some solid software engineering. But where you can use code coverage for is, if you and your team are serious about testing, then this can be a great way to gamify it. Because if you use a tool like CodeCoff, then on every pull request you generate, it will automatically see like, okay, what's going to be the diff in code coverage versus like the current state of master with this pull request, and then basically generate reports on that. Because if you're adding new code, then yeah, your code coverage at least shouldn't go down, right? This is a nice way to gamify it. So that's it about code coverage. Let's talk about test-driven development. Should you write your tests before you write your code or after? Frankly, it really doesn't matter. I don't care. Whatever works for you, just do what works for you and your team. It doesn't matter. But mind you, if you write your tests first, there's some interesting advantages. Because for every piece of code you write, you need to somehow prove that it works, right? So if you do some data processing, then how are you going to prove that it works? Sure, you can add log statements to your code and then just check the log statements, but you might as well write a test then, right? And if you write your test first, then you can also guarantee that the test would actually fail. So you're sure that the test would fail because there simply isn't an implementation yet. It also tends to be easier if you write your tests first because you're already thinking about your test if you're writing the code. It really forces you to think about the requirements up front. So imagine if I now ask you to build me a Roman numeral generator. Where on earth do you start with that, right? It's not straightforward. But surely you can come up with a simple requirement, right? Okay, so if I input 10, then I should get an x back. So that's a very simple requirement you can start with. Just write a test for that, implement it, and then think about the next requirement. So it really allows you to divide and conquer stuff. Yeah. So what is TDD? TDD is a way of working, an extreme way of working, mind you. There's just 3 simple rules you have to follow. You aren't allowed to write any code. It's a good start, right? So you aren't allowed to write any code, except if it is to make a new failing test or to make an existing failing test pass. That's the only use case when you can write code. And if you do write code, then you should write the minimum amount of code to fix the failing, to create a new failing test, and the minimum amount of code to actually, fix. So the minimum amount of code to fix a failing test, and the minimum amount of code to create a new failing test. And this actually creates this very nice red-green refactor cycle. Because you create a new test, you run it, it fails, okay? Then the next step is you're going to fix the test, You run the test, it passes, OK. And then the third step is you look at your test, and you look at your code, and you see, is there something we can simplify, improve here? And you just keep on doing the cycle over and over again. This is actually a super rewarding, super nice cycle to go through. And it has an added benefit, because if you get interrupted, or if you have to go home at the end of the day, all you have to do is stop at a failing test, and then you can completely forget about what you were working on. Because when you're going to resume your work, you just run your tests, you see one test fail, and then you know, like, OK, that's exactly where I left off. Now I can just continue working. So test-driven development, it's clear that, yeah, test-driven development is a way of developing stuff, right? But the D, you can also think of it as standing for many other things. Like, it's a way of designing your code. Because you think about the problem in different ways, you're going to end up with architectural solutions that you would never have thought about if you would just start working on it. It's a way to divide and conquer, because you can take a complex problem, split it in like a lot of small steps, and then just solve it step by step. It's a way of documentation, because if you follow this process, then you're actually going to document your train of thought. So later, if you go back to the test of that class, you can actually see like, OK, these are the steps I followed, and you can immediately see all of the requirements listed there. It's DevOps, because if you're going to run your tests so often, so you're going to run your tests when they fail, when they pass, and when you refactor, so you're actually running your tests more even than you're writing code, so then they better run fast, right? So you really need to invest in like speeding that up, because if it takes 10 seconds to run your tests, you're not going to wait 10 seconds, OK, then write one line of code, wait 10 more seconds. That simply doesn't work. It needs to be super fast. It's determination, because if you start working on a problem, us engineers, we tend to be super excited about things. So we just want to like immediately dig into the problem and start solving it. But in test-driven development, you need to refrain yourself, hold yourself back, and really follow this step-by-step process. And it's also a dream, because it's, yeah, you shouldn't test-driven develop everything. It's as simple as that. It's a great tool to solve specific cases, like if you're writing some business logic, image processing, data processing, something like in the lower layers, then TDD is pretty amazing to use. If you go more to the UI layers, then you'll see that, yeah, running UI, you need to deploy it to a device, so then your tests start getting too slow, so it's not really practical to do TDD on the UI layer, for instance. Let's do some TDD. So we aren't allowed to write any code except if it is to make a test fail or to make a failing test pass, right? So that means if we start doing TDD, we're going to write a calculator. So I'm not allowed to create a calculator class. I'm going to start with a test. I'm going to create a new test, can instantiate. So then I just create a calculator. This class doesn't exist, so now it's going to be read in Android Studio. But that's fine. You can just do Alt-Enter, and Android Studio generates the class for you. Boom. We fixed our first test. Is there something we can refactor here? No, because everything is still very simple, right? Let's add a second test. So 1 plus 3 should equal 4. OK, the sum method doesn't exist, so again, Alt-Enter in Android Studio. Now we have the method. We can run our tests. It fails because there's it to do in the method. So now we need to make the test pass. Well, what's the minimum amount of code you can write to fix this? Just return 4. OK. Is there something we can refactor here? Yeah, sure. The instantiate isn't really needed anymore, right? Because that case is also covered by the second test. So let's drop that. By the way, I didn't add any assert here. That's just for like brevity that it fits on the slide. There should be an assert in the test, right? So let's add a new test. So 2 plus 3 should equal 5. So now what's the bare minimum we can do to make the test pass? Yeah, let's just add an if statement. So if A is 1, then we return 4, else we return 5. And I'm now really ridiculizing it even, but I do that intentionally. Because TDD forces you to think about the requirements, not about the solution. You actually want to defer thinking about the solution as long as you possibly can. Because the sooner you start thinking about the solution, then you're actually already like closing yourself off to potential better solutions out there. So you really want to focus on the requirements and fix those one by one. So OK, is there something we can refactor now? No, the test pass. Let's add a third test. And let's now implement this one. Yeah, what's the simplest way to implement it? We add an other else. And we run the test, they pass. OK. Is there now something we can refactor? Yeah, maybe. What if the thing on the right, would it be possible that we can replace it with A plus B? Maybe? We run the tests, and then we see that the tests pass. So now we use T to D to actually create a very simple calculator. OK. Let's talk about some testing myths. So first and foremost, testing slows down development. Yeah, sure, it does. If you start a greenfield project and you're going to start adding tests, yeah, you're writing more code than you would do if you only write production code, right? So it definitely slows you down, sure. But then on the other hand, you need to be able to, some way or the other, you need to be able to prove that your code is doing what it's supposed to do, right? So you will have to do something. You could either do that manually or automate it. You need to do something. And if you automate it, you only have to write it once, and you can run it an infinite amount of times. So that means that if you start writing tests from day one, in 3 months from now, you don't have to manually test all of the screens in your app. You can just run all of your unit tests and already have a fairly good idea that a lot of stuff is working. So yeah, it slows down development, at least initially, but you're going to save on manual testing, and over time, you can keep going at the same speed than you were going. Testing is hard. Is writing code hard? Yeah, sure. If you're new to software, then it can be overwhelming, right? There's so much that you need to learn, but in the end, once you get used to it, writing code really isn't that hard anymore, right? And the same is true with testing. So you need to learn some new tricks. You need to learn how the testing frameworks work, what dependency injection is, about mocking. So there's a few new skills you have to learn, but yeah, once you master those, then it's just writing code. So there's no reason that, yeah, anyone in this room can do it for sure. Test code is not production code. Well, we already debunked this myth, right? So test code is production code. Think about it this way. If you write a new feature and you're going to write tests for it, what are you going to do with those tests when the feature is done? Are you going to keep them or throw them away? You're going to keep them, right? Because why would you throw them away? And if you keep something, then you have to maintain it. It's as simple as that. So you have to treat your tests with the same care as any other line of production code. Simple code shouldn't be tested. Well, I highly recommend you to look up on Google to rocket failures and see what are the main causes of rocket failures. It's this really stupid stuff like rounding errors in mathematics or unit conversions that they messed up in. So even the simplest error could have a very, very bad effect, right? So you should make sure that you test all of the important codes. Testing negatively impacts production code. I think this might be the most controversial one, but it does, right? I think one of the most common criticisms against TDD is that it forces you to create a lot of layers, so you get this overly layered architecture. And yeah, that can happen, yeah. But think about it this way. If you have a large class, that's hard to test, right? So tests kind of force you to create smaller classes. If you give methods cryptic names, then yeah, if you read your test, you're not going to make any sense of those tests. So it forces you to make better method names. If you use TDD, then you're only allowed to write code if it makes the test fail or pass. So you're going to write less code. So tests actually also force you to a lot of good stuff, like dependency injection. That's another example. So if you don't inject dependencies, you can't use a mocking framework. So there is a real negative impact in your production code, but there's also quite some positive effects. And then everything should be tested? No, it really shouldn't. So what's most important is that you have a clear strategy, right? You don't want the decision to test something to be a whim of a moment. Like today I feel like testing, tomorrow I don't, and then you just decide based on that. No. It's perfectly fine that as a team you say, for instance at Philips Hue, we say we don't test our UI. And there's plenty of other stuff we don't test, but we just say we don't do that. And then there's plenty of stuff we do test, but we have made an agreement as a team, these are the kind of things we test, these are the things we don't test. And then we can, as a team, also accept the risk. Cool. So test code versus production code. Let's analyze some extra tests, some actual tests, and see where we can improve them. So have a look at this test. So the very first thing that you may notice is like that we're extending from test case and we're prefixing our test with test underscore. This is actually the old JUnit 3 syntax. In JUnit 4 and 5, you can just add an add test annotation, and that's it. And yeah, now your test will also run. So it's way more concise. Secondly, you see this at run with Android JUnit 4 colon class. Well, this actually suggests two things. So one, it seems to imply that you're running your tests in the Android test folder, so on an emulator or physical device, which isn't required in this case. So we can just move this test from the Android test to the test folder, so it runs in a JVM, which is way faster. And secondly, this annotation actually hardly ever is necessary. The only reason why you need to use this one is if you're mixing JUnit 3 and JUnit 4 tests in the same file. If you just stick yourself to JUnit 4, you never need this annotation. So let's also drop that one. And now the test is just way simpler. So tip number one is use the JUnit 4 syntax. And by the way, JUnit 5 syntax is actually the same. You just have a different import. OK, let's have a look at this one. So here we have a setup method and then a very simple test. Now, this setup method is actually quite interesting, because now we can just for this test, we can look at the screen and we can immediately see what's going on. But imagine if we add more tests. So if you're then going to look at like the 4 tests, the setup method is going to fall off across the fault. So looking at that test, you don't know what's in the setup method anymore. So actually, the reader has to scroll up and down in order to figure out what's going on. Plus, if you start using setup methods, it also pushes you to like put other stuff in setup methods. So your setup method might get bloated with like common setup that's not needed for all of the tests, but it's like this aggregator of everything that some of the tests need. So it also makes your tests harder to read, so because you're doing more setup than you strictly need to do for your tests. So instead of doing that, why don't we just inline the setup and we do it all in one test? Now we can look at the test and we immediately see what's going on. Almost. Because the create web service, what does that do? Do we get a mock web service? Do we get a real web service? Do we do some kind of initialization? We don't know, right? Again, the reader has to leave the test in order to figure it out. So why don't we just inline that? So now you actually see, like, OK, we have a real web service, and we just configure it with an email and a password. Well, pretty straightforward, right? But this does violate one of the core principles, right? Because dry, don't repeat yourself, is something that we actively use in our production code. And then why don't we do it here? Isn't this going to cause like a lot of repetition? Yeah, it will. But the repetition isn't a bad thing per se. In your normal code, you want to avoid it. But in tests, it actually makes the tests way easier to read. Because if this test now fails, everything is contained within the same test. So repeating code in tests is perfectly fine. And then the same for check login failed, yeah. What does it do? When is a login failed? Is that result null? Is there some property on the login? Again, you would have to jump into the method to figure that out. So let's just inline that, and now we can see like, ah, yeah, if the result the result is a Boolean. If that is false, then the login has failed. So keep the reader in the test. If a test fails, the user should be able to go to the test, immediately see everything that he or she needs to know, and then be able to fix the problem. Next up, this test. Whoa, that's a lot to take in. Well, first, we have code comments. Well, code comments, yeah, they're already a code smell, except if you're documenting like why you're doing something, so there's really no reason to have them in tests. So let's just drop that one. But also, we have all of these accessibility modifiers. Why? We're not designing a public API here, right? Nobody is consuming our test classes, so it really doesn't, there is no benefit in making stuff internal or private. So let's just drop all of that clutter so we have less noise to worry about. OK, and then here, we have extracted constants for the width and height. Again, like one of these good principles for normal code, right? Don't do magic integers, don't do magic strings. But actually here, again, the same with the setup method. We have to leave the test in order to figure out what's going on. So why not just inline it? Now you can easily see, like, if the perimeter of like a square of 5 and 10, yeah, then it should be 30. So it's very easy to understand this test. So avoid clutter, because that will make your tests easier to read. Next. So here we have another test, and this is interesting. We have two asserts. So imagine if the first assert fails. Will the second one still be executed? Who thinks the second one will be executed? Whoa, really good. Nobody. So if the first one fails, the second assert won't be executed. So that actually means that this test can fail for 3 different reasons. Either is success is true, the user is not null, or both. So because the test can fail for so many reasons, it will take you way more time to figure out what was going on and to debug this problem. So let's only do one test and then just split the test in 2. But if you now look at this, yeah, it's still not clear like what method are we actually testing, what is now actually the setup, so why don't we just split it up in like an arrange act assert. So now you see the first block that does all of the setup, the second block clearly shows like, okay, we're testing the login method, and then the third block is, this is what we're actually testing. If you make all of your tests in this pattern, then you can very easily, with one glance at the test, you can very easily see what's going on. And then lastly, imagine if the test fails. So if the test fails, what's going to be printed to the console is the test name, right? But if then like login has failed is printed, yeah, what does that mean? It's so generic. So it's better to give your tests a very long method name. And on Kotlin, you can actually use spaces in method names if you put them between backticks. So this is user is null when login fails. If this gets printed, then you immediately know like, maybe login didn't fail, or maybe the user isn't null. So it, again, gives you a lot of clues of what's going on. So optimize your tests for failure. If they fail, then you need to be able to go to the test, figure out very quickly what's going on, and fix the problem very quickly. So please do repeat yourself. It's perfectly fine for tests. Magic instant strings, no problem whatsoever. Encapsulation and layering, that's all not needed. And long test names are perfectly fine. Finally, some tips. How about testing UI? On Android, we have this annoying problem where we can't create custom constructors for fragments and activities because the system might recreate them for you or just create them bluntly, and then, yeah, it won't call the custom constructor. So how do we test these? Well, actually, at least, we don't test them at all. What we do is we dumb down the view, so there's hardly any logic in it. So we use a view model from the Android architecture component, and we move all of the business and UI-related logic to that class. This class we can completely test because we can inject a repository in it, and we can also just, basically monitor live data and then see that the values are properly updated. And then what's left in the view is like very simple stuff. So the view model will report a new progress to the view, and then the view will simply do like progress bar.set progress. So that's the kind of stuff we're not testing, but it's also, it's so straightforward that it doesn't need to be tested, right? Then also, if you now look at the plain JUnit framework, it's a bit of a mess, right? Every method is called differently, and it's also like, it's always a different structure, so it doesn't really read that pleasant. So if you use AssertJ, or there's different libraries, but I prefer AssertJ, then the structure is always the same. You always say like assert that on this method, this thing is true or false. This actually is also exactly the same as what Mockito has as syntax. So verify that on this object, this method is called. So then whether you're doing behavior verification or state verification, the structure is always the same. But it's not just that, because of flipping it around, that you say like assert that on this object, now you also have autocomplete of the IDE. Because if you say assert that on a Boolean, then the IDE will just say like, is true or is false. You will only get the suggestions that are relevant for that data type. Plus, AssertJ can do tons of other cool stuff, like assert that a string ends with this value, that this list exactly contains these elements, and so on. So it has way more powerful matchers. Next up, nesting mocks. So here, it's quite verbose to read, but bear with me. So what we're testing is like whether or not we're allowed to show alcohol ads to that particular user. So we can only do that if the user is over 21 years old. So what we have is we have a user manager that returns a user, and the user has a configuration that returns age. So we actually have 3 layers of mocking in order to just make this test pass. And this is bad, because what we're doing now is we're not just, we're actually hard coding the solution or architecture to our problem in the test. We're not checking whether our code, the behavior, the functionality is actually correct. We're actually hard coding the behavior, our current solution in the test. So what would be better is if we remove these nested mocks. So instead of using the user manager, why don't we just inject the user in the alcohol ads allowed? And instead of having a configuration object on the user, why don't we flatten the data structure? So now you just have hey, mock user.class, and then if you get the age, return 21. And now this test is way simpler. Plus, we can also start refactoring the user manager without affecting these tests. So our tests are a lot less coupled with our production code. Providing test data. So this is something you need for a lot of tests. And what you could do is, for instance, here we have a class called user data. So you could just create a mock and then stop everything out. This is quite verbose, right? But there's also a problem with it, because if you now add a new property to the user data class, then your IDE won't help you to also add a new stub. So then you would manually have to look for all usages, or you're probably going to forget doing it, and then you'll have a failing test and need to figure that out. So an alternative way of doing it is you can just create a fake user data. Just instantiate the object. And if you now add a new property to that data class, then the IDE will actually tell you, hey, what default value should I use for all of the other occurrences? And then spies. So a spy is basically where you take an existing class and you kind of augment it so you can still do behavior verification on it, and you can also stub out particular behaviors. But spies, I really disencourage you to use these. Because if you have a spy and you call a method on it, it's actually gonna execute actual code. So if you have a web service and you call login on a spy of the web service, it's actually gonna do the login. So you can have one test that then creates a spy of the web service, calls login, so then it's gonna try to log in, and then the test passes, and then you go to the next test, next test, next test. At some point, your REST endpoint is gonna return you something you didn't expect, which is gonna throw an exception, and then suddenly in this test, like the 6th test or something, you're gonna see a crash because of something that happened before. This is gonna be very painful to figure out. So it's better not to use spies. And if you have dependencies you can't test, what if you're using a third-party library which has a static interface so you can't mock it, or if you're using one of the Android framework classes, what you can actually do is you can create a simple wrapper for it. So the Camera 1 API on Android, it has a complete static interface, so we can very simply create a camera wrapper, which we control and which we then can mock. And what you simply do is you implement similar methods like open native camera, and you just redirect it to the static interface. So this is a very simple class. We can't actually test it because you can't get rid of the testing problem. But now we have a layer of abstraction that we can mock in all of the other parts of our code to at least make that testable. And it's okay not to test this because at least we've isolated the problem to one single file. And then also, you don't have to unit test everything. So UI layer, you don't have to test that. Handovers between threads, I/O operations, and so on. It's perfectly fine not to test everything, as long as there is a clear strategy around it. So if you as a team say this takes us too much effort to test, fine, no problem. You don't have to automatically test it. You can do that manual later on. So let's wrap things up. I really like this quote: "We need to be as confident in the tests we code as we are in the code we test," from Xavier. Tests are production code, just like any other code, but different rules do apply. For instance, repeating yourself is not a problem. Awesome tests are blazingly fast, focused, and non-flaky. Code coverage is meaningless, and you don't need to test everything. If you want to read more, actually, I have quite a few blog posts about testing and code coverage. So by all means, have a look at those. Some image credits, because I didn't make them myself. And that was it. I'm at Monsieur on Twitter. Feel free to follow me there. And thanks for coming to my talk.